Okay, so for pulse code modulation transmitters, okay, this is how you're going to send effectively an analog signal, convert it into a digital signal, send it as a stream of ones and zeros over a communication link, which could be a radio link, it could be a fibre optic cable, it could be a metal copper cable, okay? It could be a USB cable or something like that, okay? So it can be used for a variety of different things. So what we're going to do is start off first with an analog signal, such as somebody's voice. Remember the definition for analog, it can hold any value between the power supply rails. What we're going to try and do is convert that into a digital signal and then send that through the airwaves. So, first thing we need to do is we need to make sure that none of the signal's frequencies within the signal are above half the sampling clock frequency. This sampling clock here is a clock that needs to run at least twice as fast as the highest frequency in the analog signal. If that doesn't happen, then you will get signals getting into the sampling gate and the ADC that are of too high a frequency above what we call the Nyquist limit, and that will cause a problem called aliasing, which is a form of distortion where high frequencies get reflected down to lower frequencies and cause horrible artifacts that we can't possibly have. So this low pass filter needs to make sure it cuts off absolutely every frequency above half the sampling clock frequency. Now, because we build filters that they don't go like that, they tend to go like that, they don't cut things off, that's what we call a brick wall filter. We don't tend to make filters like that. If you do make filters like that, then they cause problems with the sound. So they tend to be like that, which means we've got this sort of grey area here. So therefore we need to make sure the low pass filter leaves a bit of room so that we cut off, make sure that no frequencies above half the sampling frequency get through to the filter. So that generally means if you want to do something like CD quality, our highest frequency we hear is 20 kilohertz. So we sample at 44.1 to give it a little bit of room for the filter to have space. So the filter may be set at 20 kilohertz here, but up here we may have got to 22. So we sample at 44, so it's double this frequency, not double that frequency. Okay, that gives you that bit of room. So the sampling clock needs to take a measurement. Well, the sampling clock sets the time when a measurement of the voltage is taken. So for instance, if for a CD, it would be 44.1 thousand times a second. So to get the sampling period, we'd do 1 divided by that. That sends a signal to the sampling gate, and that then measures the voltage at that point and sends that measurement of the voltage to the analog to digital converter. Okay, so this really looks like the output of this looks just the same as a pulse amplitude modulation output. Remember those? Yeah, it just measures the height of the wave and sends it as a pulse. Sometimes people draw it like sort of go like that. Oops, not drawing properly like that, and sort of scoot them off. But in the mark schemes, they just show it as individual pulses of the same height as the wave. Okay. A lot of people would say it's actually what's called a sample and hold circuit, so it actually holds a voltage like that until that has a chance to read it. Okay? So that voltage is sent to the analog to digital converter, and that is defined as having a certain amount of bits. So this bit controls how often the sample is taken, whereas the ADC, the bit resolution of it, defines the resolution really in the y-axis, whereas that does the x-axis, if you see what I mean. Okay, so if we have an n-bit ADC, then if it's an 8-bit, for instance, it would have 256 different possible levels, or 255 steps. If it's a 16-bit, it'll have 65,536 different possible values. So by increasing the bit resolution and increasing the sampling clock, you'd also increase the amount of data that you're being produced. Okay. So that's always a trade-off in terms of how much data you want to be able to store or data that you're able to transmit. So we have the ADC set at n number of bits of resolution. That actually gives its output out. If you remember the circuit for an ADC that we do in ET5, its output gives a binary output which is in parallel format. So here we have 1, 2, 3, 4, 5, 6, 7, so that's a 7-bit ADC. So it needs 7 separate connections to the next stage, which is the piezo, parallel in, serial out. And what that does is converts the parallel information coming out side by side from the analog to digital converter into bits that can be sent one at a time. So we just get bits coming out here. Okay? That means that it has to, say this is 7-bit here, then this clock would have to run 7 times faster to control the piezo than this clock to make sure that the piezo shift register is empty before the next sample comes in. Because it's got to send 7 of them out and then the next 7 come in. 7 of them out and the next 7 come in. So this clock needs to go n times faster than that clock. Now there is an added level you can have, which is if you want to have multiple multiplexed, time division multiplexed signals, you have lots of these, each sending a different analog input, and what you do is you speed up the clock on the piezo's so it can actually handle more than one channel. So for instance, if you made that 7 times faster than that, it would do 1 channel. If you made it 70 times faster than that, you'd get 10 channels. Okay, and there's a formula on the data sheet to calculate that, time division multiplexing. Okay, they all get a separate slot. Okay, so then it's sending out 1, 0, 1, 1, 0, 1, 1, 0. This is where you get the encrypting parity bits and all that would be added and stuff if that was required, but we're not looking at that in this right now. So that's the transmitter. Nyquist limit, low pass filter prevents any signals getting in. That just about covers that, I think. So then we've got the receiver. Here we have the receiver. And what's going to happen with the receiver is this could be, travelling right across space. If it's a Sky satellite dish, the signal has travelled about 37,000 kilometres through space. On the way, it's got smaller and smaller and smaller as the signal spread out. That is called attenuation. Okay, if it's a fibre optic cable, attenuation may be caused by the glass not being completely transparent. Also, pick up noise from space or from noise in the cable or noise from around, and it could also get distorted, which would be caused by the electronics in the system itself. So you end up with a digital signal that doesn't really look quite like a digital signal anymore. It's rounded edges or it's funny shapes. So we feed it straight into our old friend, the Schmitt trigger, and that will regenerate the digital signal. If you get asked what it does, you have to put digital. It can't regenerate an analog signal because you can't tell what is noise and what is interference, what is distortion on an analog signal. You can't tell what's the information, what is the noise. Whereas a digital signal, you can. So the Schmitt trigger cleans it up and sends the data 10110 into the serial in parallel out shift register. That clock there needs to run the same speed as the clock that was sending. And if you think about when you had old modems and stuff, that handshake noise at the beginning when a modem connects is them trying to agree a speed. They try higher ones and bring it down till they get one that's stable and so on. It's called a handshake. So that needs to go the same speed as the clock that's sending. If it's multiplexing, it will need to go, say, 10 times faster again and then split the signal. So you'd have 10 of these, splitting the signal into separate phone calls or whatever it is. So the Schmitt trigger cleans it up. The CPO shift register, because it's coming in 1 bit at a time, needs to present it in a parallel format here so that it can be read by the digital to analog converter. So that converts it back into parallel format. If you remember the circuit diagram for the DAC, it had the various inputs with the different resistors that halve each time. So that's definitely a parallel input. So that's this bit here. That has the same number of bits normally as the transmitter and the same sample clock. If the sample clock was running at a different speed, then it wouldn't sound the same. You'd speed it up or slow it down, or it wouldn't work, so it has to be going at the same speed. And the DAC will then produce a step waveform that is a representation of the original analog waveform, but it has these little steps in it, and those little steps are a random error, essentially. The random error between that and the original smooth line is what we call quantization noise, or quantization error. If you have a small number of bits, then the steps are larger, so the quantization noise is louder. So by having more bits, you have less noise. That's why we have 16 bits for CD. Some people go for 24 bits when they're recording music. You can't hardly hear the difference, but you can certainly hear the difference between 16-bit and 8-bit. The DAC then turns into this waveform, and what we do then is we need to smooth this off so you can't hear the quantization noise and these little steps. And to do that, we use, the simplest way to do it is to use a low pass filter. This is a big area with digital analog converters where they have very complicated circuitry there to make it sound better, but the basic one would just have a low pass filter, sometimes called a reconstitution filter. It removes or reduces quantization error. Okay, and then at the output here, you should have a nice analog waveform coming out your headphones or whatever, listening to your music. Alright? Any questions? That covers it, doesn't it, I think?